was awesome. Okay. Yay, it's working. Awesome, the first try. So this is section 6.1, day 2. And notice I am doing on nice graph paper because here, starting mañana, you're going to have to graph things, and I'm going to show you how to graph quickly. If you got grid paper, if you're doing it on notebook paper, yeah, good luck with that. Because I can do it, but I kind of am the expert in the room on this kind of stuff, so I should be able to do it. Okay, day 2. So yesterday, we primarily talked about particle motion. I forgot to give you the worksheet. It's the one that's the goldenrod color. So those are kind of, other way around. The white one is the particle motion with integration. The goldenrod is what we're doing today. Both are AP-like questions. Those are AP. Really, they will have easy multiple choice on this. They will have hard free response on this. And they're really not hard. They're just wordy. And as soon as it gets wordy, you'll go, oh, your brain goes, hard, I ain't going to read this. What is that? But it's like, no, read it. It might be hard. It might be medium. It might be easy. But you have to actually read. And then go, oh, what calculus does this sound like? Not like, I have never read words like this before. No. Read it. Does this sound like, does this seem like, could you interpret this in any way that you have interpreted anything in calculus? Because I don't have the words they're going to use this year. I don't know. I'm doing the best I can. I'm showing you what they've said in the past. I'm trying to get you to think about how to say this stuff, how they might ask the question. But read. If they're talking about a particle moving, one time it was a squirrel on a telephone line. Squirrel's moving. Is that a particle moving? It's a thing moving. Particle, thing. If the thing is moving. If the thing is Josh, if Josh is moving, could that be our particle? Yeah. They've had somebody on a bicycle. Is the person riding the bicycle moving? Then it could be a particle motion problem. There's velocity, there's distance, there's acceleration involved. Position time, yes. I know, you just have to R-E-A-D. Okay, so going with that, it was particle motion yesterday, but today it's any change. So now we're going to talk about the big net change and future value. So big on that test. They even changed their objectives now, and one of their categories is change. That's the big idea, is change. Derivatives, is there change with derivatives? It's a rate of change. What about integration? Is there a change? Was that displacement? Was it a change in position and we got it in terms of integration? There is a whole idea, a concept, big for AP test. It's about change. It will be on that dang test. You need to understand change. So net change and future value. Is that the whole point of this? If we understand how things are changing, can we predict the future value of something? And if you can predict the future, can you make lots of money? No matter what you're doing. If you can predict something in the future, you can make money on it, right? This is what business is all about. And guess what? They don't tell them anything, but engineering is business. Businesses hire engineers. We don't do engineering just for engineering's sake. Well, wait, in academia you do. But ultimately it is to make money. Okay, so the way this works is, remember the first fundamental theorem of calculus. Do I keep coming back to that? Kind of important, right? And by the way, the second fundamental theorem of calculus is most definitely change because you're taking the derivative of a change. It's the change of a change. No, actually you're going backwards. But it's two kinds of change. We'll talk about it later. Right now, first fundamental theorem of calculus. If I integrate from A to B, and they can be times, and we have some derivative of some quantity. I'm going to call it Q for quantity now because it is not just distance. It's some sort of quantity change. If we do this, is the antiderivative of the rate of change just the amount of the thing at B minus the amount I have at A. So Q prime is how it is, some amount is changing with time. We'll say with time because that's the easiest way to think about it. So it's gallons per minute. It's feet per minute. It's pounds per minute. It's whatever the unit is, whatever the thing you are accumulating or getting rid of. One time the problem was they had sandy beach. I kid you not. Sandy beach. And they had a rate that the sand was eroding, and they had a rate that sand was being deposited. Both were derivatives. They were rates. And they wanted to know between this time and this time how much sand was accumulating on the beach. So you had to take the rate that it was leaving, subtract it from the rate that it was being added, and integrate it, and you found. So if one was tons per day and the other, they were both in units of tons per day, you subtracted the two rates, you integrated tons per day over, suppose it was, 30 days. Did you find out how much sand had accumulated on the beach in 30 days in tons? Does that make sense? So it's whatever quantity they want. And this question, there were people in line at an amusement park once. So it was people per time. And how many people went through the line in a certain amount of time at Disney World that day? Okay, you understand what I'm getting at? But what they're going to give you is they're going to give you the derivative, and it's going to be some quantity, whatever weird quantity they want per time. If you see some quantity per time and they tell you it's a rate, you think, oh, wait a minute, that's derivative. And if I want to find out how much is accumulated in a certain period of time, that's integration. Quantity, this is the rate, this is the number of people in line per hour. And if I integrate from say time 3 hours to 6 hours, is that how many people went through the line in between 3 and 6 o'clock? That's what these are all like. And they give you the weird, they're supposed to be contextual problems. It's the weirdest context I've ever seen. They're supposed to be things that you understand and can relate to. How many of you can relate to a decomposing pile of grass? Okay, at least one of you. Okay, got it. But I'm just saying, they want to do simple things like, literally, it was a pile of grass that was decomposing. Since it was decomposing, was it actually, instead of it accumulating, you were losing mass, right? Or it was weight, actually. Or was it volume? Anyway, it could be volume, it could be weight. Got it? So they do things that are supposed to be in context that you can relate to, but all I know is the kids come screaming back and they cannot relate to it. My daughter's year, it was a baked potato. It was temperature. It was not Newton's law of cooling. They gave an equation for the derivative, and how much did the temperature change of the potato over a certain period of time? It was net change future value, but it was with a baked potato. They're weird. But I just looked at them and went, did they give you a rate? And they went, yes. And that should have been the light bulb. I don't care what context it is. If it's a rate they're giving to you and they want to know how much of something you lose or gain in a certain amount of time, then it's one of these kind of problems. So what we're going to do is, every single time, this is the future value. This is the current value. This is what we know. So what we're going to do is, we're going to solve for this. Can we solve for that? Do we just add that other thing to the other side? Does it look familiar now? So what's going to happen is, if I want to find how much of this, whatever the quantity is, temperature, how the temperature has changed in the baked potato, or actually the future temperature in the baked potato, if they give me the rate, the volume of grass in my decomposing grass pile, the amount of sand on sandy beach, whatever it is, at some future time is going to be what I know now plus how much is accumulating. So if this is particle motion, I want to know the position at some future time. You're going to take the position I give you and you're going to add the displacement. So in terms of particle motion, this would be a future position, knowing a current position, or knowing a position, integrating from the known to where I want to go. So you take what you know and go to where you want to go. That's very Suzism. And we're going to integrate that rate. So every single time, this thing right here, I call it accumulation, because that's what we did in engineering, in chemical engineering. We would have a black box that was doing something, and we would do energy balances and mass balances around the thing. to see what was accumulating. Believe it or not, that's an application of this that's like definitely something that's not contextual for y'all, but it was for me, because I did that every single frickin' problem. If I didn't know what to do, I did a material and energy balance around the thing, which was this. I had some amount I started with. I integrated the description of how the heat was being transferred, or how the mass was being transferred, or the reaction, or the kinetics, or whatever it was that they were doing to the stuff inside my black box. And then I found out some future value. It was every problem in chemical engineering almost. But we had to do partial differential equations. We won't talk about that right now. That's a future problem. But it's the application. Ultimately, when we learn all this, eventually, that application. Okay, so every single time, so I did that in terms of X, but we're really doing things in terms of time, right? So our problems generally will be some future, and this is time equal to B, and I have some at some time equal to A, and I'm going to add the integration from A to B of the derivative with respect to time dt. That is the most common application, and that's how you're going to know it's one of these kind of weird problems. Huh? Yeah, but I'm saying it's not just for velocity, acceleration, and position. I'm saying that it can be for anything that's changing with time. And does everything change with time? So does that mean they can make up whatever weird problem they want? Yes, that's exactly what this means. Okay, so let's make up a weird problem. So we got weird problems. This is example 1. So example 1, we have, so I'm going to make this in terms of the number of bacteria in a petri dish. I can do anything I want, right? We can accumulate, or we can decrease an amount of anything we want. So what if the number of bacteria in my petri dish is equal to 100 at the beginning of time 0? So that means time is equal to 0, right? And then I give you that the rate that the bacteria is changing with time is equal to 90 e to the negative 0.1 t. And any of you in biology know that bacterial growth is exponential initially, but not forever. But in our course for first semester calculus, we don't get into the eventual. If you've ever look at population growth, there is usually a carrying capacity, and that's logistic growth. That's BC calculus, the second semester. We're not doing that. We're going to pretend everything's exponential. So we're just looking at early time, that it's growing exponentially or decreasing exponentially, right? Okay, so I have this rate of change, and I want to find an equation that describes the number of bacteria I have at any given time. Now, you could do the whole get the antiderivative using an indefinite integral, get a plus c, plug it in, and find it. But I want you to just try this by what we talked about yesterday, where we're going to say that the future value at any given time is equal to the current value, which I have as initial in this case, plus the accumulation or the decreasing amount. So it's the integral from this value. Notice this matches. Let me write these so you see them. This matches, right? Those match. I'm going to start from what I know, and I want to go to t. That's my unknown. That could be any time. So I'm setting you up for it so that you can do this for any problem. And then what is it? It's 90 e to the negative 0.1 t. So I just have to integrate that. Do I need to do u sub? Sure. So in reality, we're just integrating this part right here. So I know that this is equal to 100 plus 90 times the integral, and I'm going to do a u sub over here. U is equal to negative 0.1 t. What's du equal to? Negative 0.1 dt. Well, that's a negative 1/10. I don't have a negative 1/10 Well, I could make one, but I'm not going to. Does that mean I have to swing the negative 10 over to the other side? Can we do our U sub now? Okay. But I really don't want to do U sub because I have this 0 and t. I could plug them in, but I'm not. I'm just going to, over here, I'm going to do the antiderivative just so I can. So what am I doing? I'm doing the integral. Hang on. Let me make more room. I need more room. So I'm going to do the antiderivative off here to the side. So that means it's the integral of, this becomes e to the u du times negative 10. What's the antiderivative of e to the u? E to the u, right? So does this tell me that, that I'm going to need a negative 10 here, right? And I'm integrating that. I'm going to get, I know my antiderivative is e to the u, and our u was negative 0.1 t. Did y'all see what I did? I just went over here and did the antiderivative to find it, because I didn't feel like changing my limits in integration. You can if you want. I don't care. And I'm going from 0 to t. Right? This is e to the u, right? Oh, I forgot my dt. That's a dt right there. So I know that this is going to become, right? That's e to the u. So the integral of e to the u is e to the u. But I got that 10th, the negative 10 coefficient. So when I plug it all in, do I get that n of t is equal to 100, and then negative 10 times 900 is 90 is 900, and then it's going to be e to the negative 0.1 t, right? I'm going to put parentheses to show you. And then it's minus, put in the 0. What's e to the 0? Every single time. 1. I'm going to go to the next page. Is that okay? Actually, hang on. I'm going to move this page up. I'm going to move this page up. Come on, let me move you up. Okay, it's not going to let me move it up. I'll move it up later. So what did I get to? I got to the number at any given time is equal to 900 minus 900 e to the negative 0.1 t, and then it's going to be,
Is it 100 minus 100?
I got it. I was already doing the, I already moved the, okay, hang on. I moved the 900 up. There's a 900 at the back. It's 100, right? Am I minusing, am I doing negative 900 times a negative 1? Plus 900. I left off 900. Is that back one from right here? Right there. If I distribute this negative 900 times the negative 1, is that going to be plus 900? Okay, now you see where my brain jumped to. Minus the 900 e to the negative 0.1 t. I love that y'all are paying attention. So my n of t is equal to 1000 minus 900 e to the negative 0.1 t. And if I was doing this for a specific value, I would have my answer by now. Right? So that's how you do it generally. And they can do this with anything that you can integrate. And I do mean anything you can integrate. So on page 442, number 40, we're going to do that. So we're doing page, actually, let me go over here, page 442, number 40. In that problem, they give me some population. I don't remember what the problem is. I guess I should look. Hang on, I got the book right here. Okay, 442. Number 40. The population of a community of foxes is observed to fluctuate on a 10-year cycle due to variations in the availability of prey. When the population measurement begins at time 0, the population was 35 foxes. The growth rate and units of foxes per year was observed to be, and they give you a derivative. What is the population 15 years later, 35 years later? What's the population P of t at any given time greater than 0 or greater than or equal to 0? So what they're telling you is the number of foxes at time 0 is 35. The growth rate, P prime of t, is equal to 5 plus 10 sine, come here, sine of pi over 5t in foxes per year. Really, really. Oh my. If they want to know how many foxes we have in 15 years, would that be easy? P of 15 is equal to P of 0 plus the accumulation from 0 to 15. Notice where I got these from. That's my start. That's my finish. And then I put the rate in. And does this become a really easy problem? And I don't care if it's foxes per year, people in line per hour, volume of grass per day, tons of sand per day, whatever that is, whatever it is they're talking about, doesn't matter. This is the same technique every single flipping time. I need y'all to get used to reading. Whatever problem is, it's all the same problem. Okay? All right. What do we do? So it's P of 15 equals, what was the initial number of foxes? 35. Plus, what's the antiderivative of 5? 5, in this case, t. Okay, this is that little a thing. So do I need to divide by a or multiply by the reciprocal of this thing? Yeah? Remember that? If you need to go do U sub, you go do U sub on your own time. I'm not going to do U sub. So plus, and it's going to be 10 times 5 over pi, agreed? Yeah, because that's that whole 1 over a thing. And then, what is the antiderivative of sine? Whose derivative is sine? But what kind of cosine? Negative cosine. Angles have to match, right? Pi over 5t. So that's how I took account. I have the 1 over a thing. All of that evaluated between what and what? 0 and 15. By the way, this I say this is area of value, but this whole chapter is about application of integration. You now know how to integrate. Everything you've learned to integrate, I'm going to make you use. Because I can make up any silly problem I want and make the rate equal to one of the things y'all have to integrate. All right. Do you just have to evaluate it? And by the way, do not skip cosine of 0. Ever. Because what is cosine of 0? It's not 0, it's 1, right? So on these trig functions, please plug it in and make sure so you don't make a silly O. Yes? All right, so this is equal to 35 plus, so it's 15, wait, I got 5 times 15. 5 times 15 plus, that's 50 over pi, and then it's negative cosine of, okay, so pi over 5 times 15, right? And then all that put in the 0. Well, 5 times 0 is just 0. But, I'm doing the minus afterwards. 50 over pi, cosine's not so 0. Negative cosine of 0, that's not 0, is it? He's not. So let's go through this. Cosine of 0 is 1. So this whole thing's, it didn't work. Hang on. That whole thing becomes negative 1, doesn't it? This whole thing because of that negative. Yes? Agreed? That's just 0. This, I'm going to end up with, if 15 over 5, 3, this is 3 pi. What is cosine of 3 pi? It's negative 1. So that's this whole thing going to become 1, right? because it's negative of -1. You'll see where I go with this. Can we evaluate this now? Oh yeah. So this is going to equal the 35 foxes plus, what's 5 times 15? 75. And then, so this whole thing becomes positive, right? Yeah. So is that going to give me a 50 over pi? So that's plus 50 over pi. And what's this one going to give me? That's a negative of a negative. Is this also going to give me 50 over pi? So my final answer is 75 plus 35 is 110, and then plus 100 over pi. And that's my answer, and I just leave it just like that. That's about 142 foxes, and that is how you do these problems, and that would be a multiple choice question. Fair game. Now the rest of it is to add 35 in. To do 35, we just integrate from 0 to 35, and everywhere I put 15, would I put 35 in? Right? Would it be that simple? Yeah. And if we wanted to find the P of t, could we just integrate it instead of putting 15 or 35? Could I put time in? Just t? Yeah. Your mission is, okay, so there's the worksheet that's got AP-like questions. There's a few problems in the book, because the book actually does a decent job of it. Oh, let's look on the calendar for you. I'm going to stop this because we're done with notes.